This is an example video for using the first and second derivative to find critical points and concavity. We will go through an example graphically and algebraically using the following chart. First, we will look at a graph of an original function. When looking at the original function, we will want to determine where the graph is increasing and decreasing.
It looks like the graph is decreasing until some point in between x equals negative 1.7 and x equals negative 1.6. After this, it starts to increase until it reaches some point near x equals negative 0.6, where it decreases. Then it begins to increase again at x equals 0.
Perfect. So based on this analysis, where are the critical points?
I think the critical points are at about x equals negative 1.65, x equals negative 0.6, and x equals 0, because these x values are where the graph changes directions from increasing to decreasing, or vice versa.
That is correct. In this case, we cannot determine exact critical points, but we can estimate from the graph that the critical points are about x equals negative 1.65, x equals negative 0.6, and x equals 0. Let's now determine the exact critical points using calculus and algebra. The function we just analyzed the graph of is f of x equals x to the fourth plus 3x cubed plus 2x squared plus 1. To determine the critical points, we need to determine where the first derivative is equal to 0. So our first step is to take the derivative of the original function. The first derivative is f prime of x equals 4x cubed plus 9x squared plus 4x. Then we will set it equal to 0 and solve for x algebraically by factoring or using the quadratic formula. In this case, we will use the quadratic formula as the function cannot be easily factored.
So now that we have solved the equation, can we say that the critical points occur at x equals negative 1.64, negative 6.1, and 0?
Yes, we can.
So what do we use the critical points for?
We know that these points are where the slope of the tangent line of the original function is equal to 0.
Okay, I understand what these points look like in the original function, but what do these points look like on the graph of the first derivative?
That's a great question. The graph of the first derivative looks like this.
Oh, I see that the graph of the first derivative crosses the x-axis at each of the points we found.
That's correct. Also notice that the graph of the first derivative also has points where the slope of the tangent line is equal to 0. What do you think these points represent?
Well, based on the chart that we have been using, I think that these points are the inflection points of the original function.
You're right. We can see the points where the tangent line is equal to 0, or where the graph changes direction, are roughly equal to x equals negative 1.23 and x equals negative 0.27.
Can we solve for these points algebraically like we did when we found the critical points?
Yes, the process for finding inflection points requires the same steps, but instead of finding the zeros of the first derivative, we need to find the zeros of the second derivative. Our first step is to take the derivative of the first derivative, which is f double prime of x equals 12x squared plus 18x plus 4. We then will set the function equal to 0. We cannot easily factor this equation to solve for x, so we will need to use the quadratic formula again to find the zeros. We find that the zeros are approximately x equals negative 1.2287 and x equals negative 0.27129.
Okay, I think I understand. To find the critical points, we take the first derivative of the original function, set it equal to 0, and find what x is equal to. To find the inflection points, we set the second derivative equal to 0 and find the x values again.
Exactly.